ReAct, Synergizing Reasoning and Acting in Language Models. There are 7 authors, including Shunyu Yao from Department of Computer Science, Princeton University, Jeffrey Zhao, Dian Yu, Nan Du, Izhak Shafran from Google Research. While large language models, LLMs, have demonstrated impressive performance across tasks in language understanding and interactive decision-making, their abilities for reasoning, e.g., chain of thought prompting, and acting, e.g., action plan generation, have primarily been studied as separate topics. In this paper, we explore the use of LLMs to generate both reasoning traces and task-specific actions in an interleaved manner, allowing for greater synergy between the two. Reasoning traces help the model induce, track, and update action plans, as well as handle exceptions, while actions allow it to interface with and gather additional information from external sources such as knowledge bases or environments. We apply our approach, named ReAct, to a diverse set of language and decision-making tasks and demonstrate its effectiveness over state-of-the-art baselines, in addition to improved human interpretability and trustworthiness. Concretely, on question answering, hotpot QA, and fact verification, fever, ReAct overcomes prevalent issues of hallucination and error propagation in chain-of-thought reasoning by interacting with a simple Wikipedia API and generating human-like task-solving trajectories that are more interpretable than baselines without reasoning traces. Furthermore, on 2 interactive decision-making benchmarks, ALFworld and WebShop, ReAct outperforms imitation and reinforcement learning methods by an absolute success rate of 34% and 10% respectively, while being prompted with only 1 or 2 in-context examples. 1. Introduction. A unique feature of human intelligence is the ability to seamlessly combine task-oriented actions with verbal reasoning, which has been theorized to play an important role in human cognition for enabling self-regulation or strategization and maintaining a working memory. Consider the example of cooking up a dish in the kitchen. Between any 2 specific actions, we may reason in language in order to track progress. Now that everything is cut, I should heat up the pot of water to handle exceptions or adjust the plan according to the situation. I don't have salt, so let me use soy sauce and pepper instead. And to realize when external information is needed, how do I prepare dough? Let me search on the internet. We may also act, open a cookbook to read the recipe, open the fridge, check ingredients, to support the reasoning and to answer questions. What dish can I make right now? This tight synergy between acting and reasoning allows humans to learn new tasks quickly and perform robust decision-making or reasoning, even under previously unseen circumstances or facing information uncertainties. Recent results have hinted at the possibility of combining verbal reasoning with interactive decision-making in autonomous systems. On one hand, properly prompted large language models, LLMs, have demonstrated emergent capabilities to carry out several steps of reasoning traces to derive answers from questions in arithmetic, common sense, and symbolic reasoning tasks. However, this chain of thought reasoning is a static black box, in that the model uses its own internal representations to generate thoughts and is not grounded in the external world, which limits its ability to reason reactively or update its knowledge. This can lead to issues like fact hallucination and error propagation over the reasoning process, Figure 1.1b. On the other hand, recent work has explored the use of pre-trained language models for planning and acting in interactive environments, with a focus on predicting actions via language priors. These approaches usually convert multimodal observations into text, use a language model to generate domain-specific actions or plans, and then use a controller to choose or execute them. However, they do not employ language models to reason abstractly about high-level goals or maintain a working memory to support acting, barring those who perform a limited form of verbal reasoning to reiterate spatial facts about the current state. Beyond such simple embedded tasks to interact with a few blocks, there have not been studies on how reasoning and acting can be combined in a synergistic manner for general task solving, and if such a combination can bring systemic benefits compared to reasoning or acting alone.
Figure 1 summary. This figure compares 4 prompting methods for solving tasks: standard, chain of thought, COT, reason only, act only, and ReAct, reason plus act. It includes 2 domains: solving a hotpot QA question and an ALF world game. In hotpot QA, the methods are shown in terms of task-solving trajectories generated by the model, focusing on reasoning and actions. In ALF world, it contrasts act-only and ReAct prompting, highlighting how ReAct combines reasoning and actions for improved task performance. The figure illustrates how ReAct integrates reasoning and acting to enhance decision-making and task-solving capabilities.
In this work, we present ReAct, a general paradigm to combine reasoning and acting with language models for solving diverse language reasoning and decision-making tasks. Figure 1. ReAct prompts LLMs to generate both verbal reasoning traces and actions pertaining to a task in an interleaved manner, which allows the model to perform dynamic reasoning to create, maintain, and adjust high-level plans for acting, reason to act, while also interact with the external environments, e.g. Wikipedia, to incorporate additional information into reasoning, act to reason. We conduct empirical evaluations of ReAct and state-of-the-art baselines on 4 diverse benchmarks: question answering, fact verification, text-based game, and web page navigation. For Hotpot QA and Fever, with access to a Wikipedia API that the model can interact with, ReAct outperforms vanilla action generation models while being competitive with chain-of-thought reasoning. The best approach overall is a combination of ReAct and COT that allows for the use of both internal knowledge and externally obtained information during reasoning. On ALF World and WebShop, 2 or even one-shot ReAct prompting is able to outperform imitation or reinforcement learning methods trained with 10 to the power of 3 to 10 to the power of 5 task instances, with an absolute improvement of 34% and 10% in success rates, respectively. We also demonstrate the importance of sparse, versatile reasoning in decision-making by showing consistent advantages over controlled baselines with actions only. Besides general applicability and performance boost, the combination of reasoning and acting also contributes to model interpretability, trustworthiness, and diagnosability across all domains. As humans can readily distinguish information from models' internal knowledge versus external environments, as well as inspect reasoning traces to understand the decision basis of model actions. To summarize, our key contributions are the following. 1. We introduce ReAct, a novel prompt-based paradigm to synergize reasoning and acting in language models for general task solving. 2. We perform extensive experiments across diverse benchmarks to showcase the advantage of ReAct in a few-shot learning setup over prior approaches that perform either reasoning or acting generation in isolation. 3. We present systematic ablations and analysis to understand the importance of acting in reasoning tasks and reasoning in interactive tasks. 4. We analyze the limitations of ReAct under the prompting setup, i.e., limited support of reasoning and acting behaviors, and perform initial fine-tuning experiments showing the potential of ReAct to improve with additional training data. Scaling up ReAct to train and operate on more tasks and combining it with complementary paradigms like reinforcement learning could further unlock the potential of large language models. 2. ReAct, synergizing reasoning plus acting. Consider a general setup of an agent interacting with an environment for task solving. At time step t, an agent receives an observation O sub t in O from the environment and takes an action A sub t in A, following some policy pi of A sub t given C sub t, where C sub t equals open parenthesis O sub 1 A sub 1 up to O sub t minus 1 A sub t minus 1, O sub t close parenthesis is the context to the agent. Learning a policy is challenging when the mapping from C sub t to A sub t is highly implicit and requires extensive computation. For example, the agent shown in Figure 1c is unable to generate the correct final action, Act 4, to finish the QA task as it requires complex reasoning over the trajectory context. Question Act 1 through 3, OBES 1 through 3. Similarly, the agent shown in Figure 1a fails to comprehend from the context that Sync Basin 1 does not contain Papershark 1, thus keep producing hallucinating actions. The idea of ReAct is simple. We augment the agent's action space to A hat equals A union C, where L is the space of language. An action a hat subscript T in L in the language space, which we will refer to as a thought or a reasoning trace, does not affect the external environment, thus leading to no observation feedback. Instead, a thought a hat subscript T aims to compose useful information by reasoning over the current context, C subscript T, and update the context C subscript T plus 1 equals open parenthesis, C subscript T, comma, a hat subscript T, close parenthesis, to support future reasoning or acting. As shown in Figure 1, there could be various types of useful thoughts. For example, decomposing task goals and create action plans. Open parenthesis 2b, comma, act 1 semicolon, ID 1d semicolon. Thought 1, close parenthesis, injecting common sense knowledge relevant to task solving. Open parenthesis 2b, comma, act 1, close parenthesis, extracting important parts from observations. Open parenthesis 1d, comma. Thought 2, close parenthesis, track progress and transit action plans. Open parenthesis 2b, comma, act B, close parenthesis. Handle exceptions and adjust action plans. Open parentheses, I, comma, thought 3, close parentheses, and so on. However, as the language space L is unlimited, learning in this augmented action space is difficult and requires strong language priors. In this paper, we mainly focus on the setup where a frozen large language model, Palm 540B, is provided with few-shot in-context examples to generate both domain-specific actions and free-form language thoughts for task solving, Figure 1. Each in-context example is a human trajectory of actions, thoughts, and environment observations to solve a task instance. For the tasks where reasoning is of primary importance, Figure 1, we alternate the generation of thoughts and actions so that the task-solving trajectory consists of multiple thought-action-observation steps. In contrast, for decision-making tasks that potentially involve a large number of actions, Figure 1, thoughts only need to appear sparsely in the most relevant positions of a trajectory, so we let the language model decide the asynchronous occurrence of thoughts and actions for itself. Since decision-making and reasoning capabilities are integrated into a large language model, ReAct enjoys several unique features. A. Intuitive and easy to design. Designing ReAct prompts is straightforward as human annotators just type down their thoughts in language on top of their actions taken. No ad hoc format choice, thought design, or example selection is used in this paper. We detail prompt design for each task in sections 3 and 4. B. General and flexible. Due to the flexible thought space and thought action occurrence format, ReAct works for diverse tasks with distinct action spaces and reasoning needs, including but not limited to QA, fact verification, text game, and web navigation. C. Performant and robust. ReAct shows strong generalization to new task instances while learning solely from 1 to 6 in-context examples, consistently outperforming baselines with only reasoning or acting across different domains. We also show in Section 3 additional benefits when fine-tuning is enabled, and in Section 4 how ReAct performance is robust to prompt selections. D. Human-aligned and controllable. ReAct promises an interpretable sequential decision-making and reasoning process where humans can easily inspect reasoning and factual correctness. Moreover, humans can also control or correct the agent behavior on the go by thought editing, as shown in Figure 5 in Section 4.
Figure 5 summary. This image consists of 2 panels illustrating a human-in-the-loop behavior correction scenario using ReAct in AlfWorld. Panel A depicts a ReAct trajectory that fails due to a hallucinated thought at Act 17. Panel B shows the correction process where a human edits 2 thoughts at Acts 17 and 23, leading to successful reasoning and actions. The example highlights how human intervention can adjust the reasoning process to achieve desired outcomes, demonstrating the potential for human collaboration in refining AI behavior.
3 knowledge-intensive reasoning tasks. We begin with knowledge-intensive reasoning tasks like multi-hop question answering and fact verification. As shown in Figure 1D, by interacting with a Wikipedia API, ReAct is able to retrieve information to support reasoning, while also use reasoning to target what to retrieve next, demonstrating a synergy of reasoning and acting. 3.1 Setup. Domains. We consider 2 datasets challenging knowledge retrieval and reasoning. 1. Hotpot QA, a multi-hop question answering benchmark that requires reasoning over 2 or more Wikipedia passages. And 2, Fever, a fact verification benchmark where each claim is annotated. Supports, refutes, or not enough info, based on if there exists a Wikipedia passage to verify the claim. In this work, we operate in a question-only setup for both tasks, where models only receive the question claim as input without access to question paragraphs, and have to rely on their internal knowledge or retrieve knowledge via interacting with an external environment to support reasoning. Action space. We design a simple Wikipedia web API with 3 types of actions to support interactive information retrieval. 1. Search entity, which returns the first 5 sentences from the corresponding entity wiki page if it exists, or else suggests top 5 similar entities from the Wikipedia search engine. 2. Lookup string, which would return the next sentence in the page containing string, simulating Control-F functionality on the browser. 3. Finish answer, which would finish the current task with answer. We note that this action space mostly can only retrieve a small part of a passage based on exact passage name, which is significantly weaker than state-of-the-art lexical or neural retrievers. The purpose is to simulate how humans would interact with Wikipedia and force models to retrieve via explicit reasoning in language. 3.2 Methods. ReAct prompting for Hotpot QA and Fever. We randomly select 6 and 3 cases squared from the training set and manually compose ReAct format trajectories to use as few-shot exemplars in the prompts. Similar to Figure 1D, each trajectory consists of multiple thought-action observation steps, i.e. dense thought, where free-form thoughts are used for various purposes. Specifically, we use a combination of thoughts that decompose questions. I need to search X, find Y, then find Z. Extract information from Wikipedia observations. X was started in 1844. The paragraph does not tell X. Perform common sense. X is not Y, so Z must instead be, or arithmetic reasoning. 1844 is less than 1989. Guide. Search reformulation. Maybe I can search look up X instead, and synthesize the final answer, so the answer is X. See Appendix C for more details. Baselines. We systematically ablate ReAct trajectories to build prompts for multiple baselines with formats as figure LA through LC, a standard prompting standard, which removes all thoughts, actions, observations in ReAct trajectories. B. Chain of thought prompting CoT, which removes actions and observations and serve as a reasoning-only baseline. We also build a self-consistency baseline CoSC by sampling 21 CoT trajectories with decoding temperature 0.7 during inference and adopting the majority answer, which is found to consistently outperform COT. C. Acting-only prompt ACT, which removes thoughts in ReAct trajectories, loosely resembling how WebGPT interacts with the internet to answer questions, though it operates on a different task and action space and uses imitation and reinforcement learning instead of prompting. Combining internal and external knowledge. As will be detailed in section 3.3, we observe that the problem-solving process demonstrated by ReAct is more factual and grounded, whereas CoT is more accurate in formulating reasoning structure, but can easily suffer from hallucinated facts or thoughts. We therefore propose to incorporate ReAct and CoTSC and let the model decide when to switch to the other method based on the following heuristics. A. ReAct, CoTSC. When ReAct fails to return an answer within given steps, back off to CoTSC. We set 7 and 5 steps for Hotpot QA and Fever respectively, as we find more steps will not improve ReAct performance. B. CoTSC to ReAct when the majority answer among n CoTSC samples occurs less than n divided by 2 times, i.e. internal knowledge might not support the task confidently. Back off to ReAct. Fine-tuning. Due to the challenge of manually annotating reasoning traces and actions at scale, we consider a bootstrapping approach similar to Seligman et al., using 3,000 trajectories with correct answers generated by ReAct, also for other baselines, to fine-tune smaller language models, Palm 6/62b, to decode trajectories, all thoughts, actions, observations conditioned on input questions/claims. More details are in Appendix B.1. 3.3 Results and Observations. ReAct outperforms ACT consistently. Table 1 shows Hotpot QA and Fever results using Palm 540B as the base model with different prompting methods. We note that ReAct is better than ACT on both tasks, demonstrating the value of reasoning to guide acting, especially for synthesizing the final answer, as shown in figure DCL. Fine-tuning results also confirm the benefit of reasoning traces for more informed acting. ReAct versus COT. On the other hand, ReAct outperforms COT on Fever 60.9 versus 56.3 and slightly lags behind COT on Hotpot QA 27.4 versus 29.4. Fever claims for supports or refutes might only differ by a slight amount, see Appendix D.1, so acting to retrieve accurate and up-to-date knowledge is vital. To better understand the behavioral difference between ReAct and COT on Hotpot QA, we randomly sampled 50 trajectories with correct and incorrect answers, judged by EM from ReAct and COT respectively, thus 200 examples in total, and manually labeled their success and failure modes in Table 2. Some key observations are as follows. A. Hallucination is a serious problem for COT, resulting in much higher false positive rate than ReAct, 14% versus 6%, in success mode, and make up its major failure mode, 56%. In contrast, the problem-solving trajectory of ReAct is more grounded, fact-driven, and trustworthy, thanks to the access of an external knowledge base.
Table 2 summary. The table compares success and failure modes of ReAct and COT on Hotpot QA. ReAct has a higher success rate, 94%, compared to COT, 86%. COT experiences more hallucinations, with a 14% false positive rate and 56% failure due to hallucinated reasoning, whereas ReAct has 6% false positives and no failures from hallucinations. ReAct shows a higher reasoning error rate, 47% compared to COT, 16%, and a 23% search result error rate, which COT does not have. Label ambiguity is similar for both at around 28 to 29%.
B. While interleaving reasoning, action and observation steps improves ReAct's groundedness and trustworthiness. Such a structural constraint also reduces its flexibility in formulating reasoning steps, leading to more reasoning error rate than COT. We note that there is no independent error pattern specific to ReAct, in which the model repetitively generates the previous thoughts and acts that we categorize it as part of reasoning error. As the model fails to reason about what the proper next action to take and jump out of the loop. C. For ReAct, successfully retrieving informative knowledge via search is critical. Non-informative search, which counts for 23% of the error cases, derails the model reasoning and gives it a harder to recover and reformulate thoughts. This is perhaps an expected trade-off between factuality and flexibility, which motivates our proposed strategies of combining two methods. We provide examples for each success and failure modes in Appendix E.1. We also find some Hotpot QA questions may contain outdated answer labels. See Figure 4, for example.
Figure 4 summary. This figure illustrates a Hotpot QA question where the original answer is outdated. It shows how different models respond to a question about the number of rooms in a hotel associated with Cirque du Soleil. The standard and COT models provide incorrect answers due to outdated information or hallucination, while the ACT model fails despite having web interaction capabilities. Only the ReAct model successfully retrieves the up-to-date answer by effectively using real-world web interaction combined with reasoning. This highlights the importance of reasoning abilities in internet-augmented language models for providing current and accurate information.
ReAct plus COT TSC perform best for prompting LLMs. Also shown in Table 1, the best prompting method on Hotpot QA and Fever are ReAct followed by CoTSC and CoTSC followed by ReAct respectively. Furthermore, Figure 2 shows how different methods perform with respect to the number of COT-SC samples used. While two ReAct plus CoTSC methods are advantageous at one task each, they both significantly and consistently outperform CoSC across different number of samples, reaching CoTSC performance with 21 samples using merely 3 to 5 samples. These results indicate the value of properly combining internal knowledge and external knowledge for reasoning tasks.
Table 1 summary. The table compares various prompting methods on Hotpot QA and Fever tasks using Palm 540B. The ReAct COD-SC method achieves the highest performance on Hotpot QA with 35.1 EM, while COD-SC plus ReAct performs best on Fever with 64.6% accuracy. The supervised SOTA significantly outperforms all prompting methods with 67.5 EM on Hotpot QA and 89.5% accuracy on Fever. Table 1 Summary. The table presents a series of observations and thoughts regarding two mathematicians, Pavel Samuilovich Urisohn and Leonid Anatolievich Levin. Urisohn is noted for his contributions to dimension theory, while Levin is identified as a mathematician and computer scientist. The conclusion drawn is that both individuals share a similar type of work in mathematics.
ReAct performs best for fine-tuning. Figure 3 shows the scaling effect of prompting or fine-tuning four methods: standard, COT, ACT, ReAct on Hotpot QA. With Palm 62 billion or 8 billion, prompting ReAct performs worst among four methods due to the difficulty to learn both reasoning and acting from in-context examples. However, when fine-tuned with just 3,000 examples, ReAct becomes the best method among the four. With Palm 8 billion fine-tuned ReAct outperforming all Palm 62 billion prompting methods, and Palm 62 billion fine-tuned ReAct outperforming all 540 billion prompting methods. In contrast, fine-tuning standard or COT is significantly worse than fine-tuning ReAct or ACT for both Palm 8 or 62 billion, as the former essentially teaches models to memorize potentially hallucinated knowledge facts, and the latter teaches models how to reason and act to access information from Wikipedia, a more generalizable skill for knowledge reasoning. As all prompting methods are still significantly far from domain-specific state-of-the-art approaches, Table 1, we believe fine-tuning with more human-written data might be a better way to unleash the power of ReAct.
Figure 3 Summary. This figure presents a bar graph comparing the effectiveness of different learning methods, namely prompting and fine-tuning, on the Hotpot QA dataset using the ReAct model and baseline models. The graph is divided into three sections based on model sizes: 8 billion, 62 billion, and 540 billion parameters. Each section shows the performance of learning methods with ReAct, ACT, and other baselines compared. The graph indicates that ReAct generally performs better across different model sizes, especially in larger models, highlighting its scalability and effectiveness in improving model performance.
4. Decision-making tasks. We also test ReAct on two language-based interactive decision-making tasks, ElfWorld and WebShop, both of which feature complex environments that require agents to act over long horizons with sparse rewards, warranting the need for reasoning to act and explore effectively. ElfWorld. ElfWorld is a synthetic text-based game designed to align with the embodied Alfred benchmark. It includes 6 types of tasks in which an agent needs to achieve a high-level goal. For example, examine paper under desk lamp by navigating and interacting with a simulated household via text actions. For example, go to coffee table 1, take paper 2, use desk lamp 1. A task instance can have more than 50 locations and take an expert policy more than 50 steps to solve, thus challenging an agent to plan and track sub-goals as well as explore systematically. For example, check all desks one by one for desk lamp. In particular, one challenge built into ElfWorld is the need to determine likely locations for common household items. For example, desk lamps will likely be on desks, shelves, or dressers, making this environment a good fit for LLMs to exploit their pre-trained common sense knowledge. To prompt ReAct, we randomly annotate the trajectories from the training set for each task type, where each trajectory includes sparse thoughts that 1. Decompose the goal, 2. Track sub-goal completion, 3. Determine the next sub-goal, and 4. Reason via common sense where to find an object and what to do with it. We show prompts used for ElfWorld in Appendix C.4. We evaluate on 134 task instances per task in a task-specific setup. For robustness, we construct 6 prompts for each task type through each permutation of 2 annotated trajectories from the 3 we annotate. ACT prompts are constructed using the same trajectories, but without thoughts. Since task instances are randomly chosen from the training set, It favors neither ReAct nor ACT and provides a fair and controlled comparison to test the importance of sparse thoughts. For baselines, we use Butler, an imitation learning agent trained on 10, raised to the power of 6 expert trajectories for each task type. Web Shop. Can ReAct also interact with noisy real-world language environments for practical applications? We investigate Web Shop, a recently proposed online shopping website environment with 1.18 million real-world products and 12,000 human instructions. Unlike ALF World, WebShop contains a high variety of structured and unstructured texts, e.g. product titles, descriptions, and options crawled from Amazon, and requires an agent to purchase a product based on a user instruction, e.g., I am looking for a nightstand with drawers. It should have a nickel finish and priced lower than $140 through web interactions, e.g. search nightstand drawers, choose buttons such as color, modern nickel white, or back to search. This task is evaluated by average score, percentage of desired attributes covered by the chosen product, averaged across all episodes, and success rate, percentage of episodes where the chosen product satisfies all requirements on 500 test instructions. We formulate ACT prompts with actions to search, choose product, choose options, and buy, with ReAct prompts additionally reasoning to determine what to explore, when to buy, and what products options are relevant to the instruction. See Table 6 for an example prompt, and Table 10 for model predictions in the appendix. We compare to an imitation learning method, trained with 1,012 human annotated trajectories, and an imitation plus reinforcement learning, IL plus RL, method, additionally trained with 10,587 training instructions. Results: ReAct outperforms ACT on both ALF World, Table 3, and WebShop, Table 4. On ALF World, the best ReAct trial achieves an average success rate of 71%, significantly outperforming the best ACT 45% and Butler 37% trials. In fact, even the worst ReAct trial, 48%, beats the best trial of both methods. Moreover, the advantage of ReAct over ACT is consistent across 6 controlled trials, with relative performance gain ranging from 33% to 90% and averaging 62%. Qualitatively, we saw that, without any thoughts at all, ACT fails to correctly decompose goals into smaller subgoals or loses track of the current state of the environment. Example trajectories comparing ReAct and ACT can be found in Appendix D.2.1 and Appendix D.2.2.
Table 3 Summary. The table presents task-specific success rates for different methods on ALF World tasks. ReAct Best of 6 achieves the highest overall success rate at 71%, outperforming ACT Best of 6 at 45%, and Butler Best of SAC 6 at 37%. ReAct also performs well with a 57% success rate. ReAct IM Best of 6 shows moderate performance at 53%. Butler Best of S has the lowest success rate at 22%. The results highlight the effectiveness of ReAct methods over others in task completion. Table 4 Summary. The table compares the performance of different methods on the WebShop task. ReAct achieves a higher score, 66.6, and success rate 40.0 compared to ACT 62.3 score, 30.1 SR, IL 59.9 score, 29.1 SR, and IL plus RL 62.4 score, 28.7 SR. Human performance is significantly higher with a score of 82.1 and a success rate of 59.6.
On WebShop, one-shot ACT prompting already performs on par with IL and IL plus RL methods. With additional sparse reasoning, ReAct achieves significantly better performance, with an absolute 10% improvement over the previous best success rate. By checking examples, we find that ReAct is more likely to identify instruction-relevant products and options by reasoning to bridge the gap between noisy observations and actions, e.g., for space-saving ottoman bench for living room, the item has options 39 by 18 by 18 inch and blue, and seems good to buy. However, existing methods are still far from the performance of expert humans, Table 4, who perform significantly more product explorations and query reformulations that are still challenging for prompting-based methods. On the value of internal reasoning versus external feedback. To our knowledge, ReAct is the first demonstration of combined reasoning and action using an LLM applied to an interactive environment within a closed-loop system. Perhaps the closest prior work is Inner Monologue, IM, from Huang et al., in which actions from the embodied agent are motivated by an eponymous inner monologue. However, IM's inner monologue is limited to observations of the environment state and what needs to be completed by the agent for the goal to be satisfied. In contrast, the reasoning traces in ReAct for decision-making is flexible and sparse, allowing diverse reasoning types to be induced for different tasks. To demonstrate the differences between ReAct and IM, and to highlight the importance of internal reasoning versus simple reactions to external feedback, we ran an ablation experiment using a thought pattern composed of IM-like cues, external feedback. As can be seen in Table 3, ReAct substantially outperforms IM-style prompting, ReAct IM, 71 versus 53 overall success rate, with consistent advantages on 5 out of 6 tasks. Qualitatively, we observed that ReAct IM often made mistakes in identifying when sub-goals were finished, or what the next sub-goal should be, due to a lack of high-level goal decomposition. Additionally, many ReAct IM trajectories struggled to determine where an item would likely be within the ELF world environment due to a lack of common-sense reasoning. Both shortcomings can be addressed in the ReAct paradigm. More details about ReAct IM is in Appendix B.2. An example prompt for ReAct IM can be found in Appendix C.4 and an example trajectory in Appendix D.2.3. 5. Related work. Language model for reasoning. Perhaps the most well-known work of using LLMs for reasoning is Chain of Thought, COAT, which reveals the ability of LLMs to formulate their own thinking procedure for problem solving. Several follow-up works have since been performed, including least to most prompting for solving complicated tasks, zero-shot COT, and reasoning with self-consistency. Recently, systematically studied the formulation and structure of COT and observed that the presence of symbols, patterns, and texts is crucial to the effectiveness of COAT. Other work has also been extended to more sophisticated reasoning architecture beyond simple prompting. For example, selection inference divides the reasoning process into 2 steps of selection and inference. STAR bootstraps the reasoning process by fine-tuning the model on correct rationales generated by the model itself. Faithful reasoning decomposes multi-step reasoning into 3 steps, each performed by a dedicated LM respectively. Similar approaches like Scratchpad, which fine-tunes a LM on intermediate computation steps, also demonstrate improvement on multi-step computation problems. In contrast to these methods, ReAct performs more than just isolated fixed reasoning and integrates model actions and their corresponding observations into a coherent stream of inputs for the model to reason more accurately and tackle tasks beyond reasoning, e.g., interactive decision-making. Language model for decision-making. The strong capability of LLMs has enabled them to perform tasks beyond language generation, and it is becoming more popular to take advantage of LLMs as a policy model for decision-making, especially in interactive environments. WebGPT uses an LM to interact with web browsers, navigate through web pages, and infer answers to complicated questions from ILEs. In comparison to ReAct, WebGPT does not explicitly model the thinking and reasoning procedure, instead rely on expensive human feedback for decision-making. In conversational modeling, chatbots like BlenderBot and Sparrow, and task-oriented dialogue systems like SimpleTod also train LMs to make decisions about API calls. Unlike ReAct, they do not explicitly consider the reasoning procedure, and thus also relies on expensive datasets and human feedback collection for policy learning. In contrast, ReAct learns a policy in a much cheaper way, since the decision-making process only requires language description of the reasoning procedure. LLMs have also been increasingly employed in interactive and embodied environments for planning and decision-making. Perhaps most relevant to ReAct in this respect are SayCan and Inner Monologue, which use LLMs for robotic action planning and decision-making. In SayCan, LLMs were prompted to directly predict possible actions over a robot's actions. This is then re-ranked by an affordance model grounded on the visual environments for final prediction. Inner Monologue made further improvements by adding the eponymous Inner Monologue, which is implemented as injected feedback from the environment. To our knowledge, inner monologue is the first work that demonstrates such a closed-loop system, which ReAct builds on. However, we argue that inner monologue does not truly comprise of inner thoughts. This is elaborated in Section 4. We also note that leveraging language as semantically rich inputs in the process of interactive decision-making has been shown to be successful under other settings. It is becoming more evident that with the help of LLMs, language as a fundamental cognitive mechanism will play a critical role in interaction and decision-making. What is more, progress in LLMs has also inspired the development of versatile and generalist agents like Read et al. 6. Conclusion. We have proposed ReAct, a simple yet effective method for synergizing reasoning and acting in large language models. Through a diverse set of experiments on multi-hop question answering, fact-checking, and interactive decision-making tasks, we show that ReAct leads to superior performance with interpretable decision traces. Despite the simplicity of our method, complex tasks with large action spaces require more demonstrations to learn well, which unfortunately can easily go beyond the input length limit of in-context learning. We explore the fine-tuning approach on Hotpot QA with initial promising results, but learning from more high-quality human annotations will be the desiderata to further improve the performance. Scaling up ReAct with multitask training and combining it with complementary paradigms like reinforcement learning could result in stronger agents that further unlock the potential of LLMs for more applications. Reproducibility statement. Our main experiments are done on Palm, which is not an openly accessible model yet. To increase reproducibility, we have included all used prompts in Appendix C, additional experiments using GPT-3 in Appendix A.1, and associated GPT-3 ReAct prompting code at CURL in paper. Ethics statement. ReAct prompts large language models to generate more human interpretable, diagnosable, and controllable task-solving trajectories than previous methods. However, hooking up a large language model with an action space to interact with external environments, e.g. the web, physical environments, has potential dangers, e.g. looking up inappropriate or private information or taking harmful actions in an environment. Our experiments minimize such risks by limiting the interactions to specific websites, Wikipedia or WebShop, that are free of private information, without any dangerous actions in the action space design, i.e. models cannot really buy products on WebShop, the research benchmark, or edit Wikipedia. We believe researchers should be aware of such risks before designing more extensive experiments in the future. You have reached the end of the main paper. Appendix sections follow. Additional results. A1 GPT-3 experiments. Table 5. ReAct prompting results using Palm 540B versus GPT-3. Text DaVinci 002, greedy decoding. On Hotpot QA, we randomly sample a subset of 500 validation questions. On AlfWorld, we use all 134 unseen validation task instances and use the best prompt set according to Palm 540B.
Table 5 Summary. The table compares the performance of Palm 540B and GPT-3 on two tasks, Hotpot QA and AlfWorld. GPT-3 slightly outperforms Palm 540B on Hotpot QA with an exact match score of 30.8 compared to 29.4. On AlfWorld, GPT-3 also shows a higher success rate of 78.4% compared to 70.9% for Palm 540B. This suggests that GPT-3 is more effective in these tasks, potentially due to its fine-tuning with human instruction following.
We run additional GPT-3 experiments to confirm ReAct prompting performance is general across different large language models. As shown in Table 5, GPT-3, Text DaVinci 002 greedy decoding consistently outperforms Palm 540B on Hotpot QA and AlfWorld, possibly because it is fine-tuned with human instruction following. This indicates ReAct prompting is effective across different large language models on different tasks. The code for these experiments are at CURL in paper. A2. ReAct obtains up-to-date knowledge on Hotpot QA. During trajectory inspection, we also find that sometimes ReAct does not agree with dataset labels as the labels themselves could be outdated. For example, as shown in Figure 4, The question asks about the size of a hotel, which increased from the Hotpot QA construction time. While Standard and CoT give wrong answers due to hallucination, ACT fails despite the access of real-world web interaction due to a lack of reasoning to guide how to interact with the internet for QA. Only ReAct is able to retrieve up-to-date information from the internet and provide a reasonable answer. Therefore, better incorporation of reasoning abilities might benefit recent internet augmented language models for up-to-date task solving. A3. Human-in-the-loop behavior correction on AlfWorld. We also explore human-in-the-loop interaction with ReAct to allow a human to inspect and edit ReAct's reasoning traces. Figure 5 shows that by simply removing a hallucinating sentence in Act 17 and adding some hints in Act 23, ReAct can be made to change its behavior drastically to align with these human thought edits and succeed in the task. From a human perspective, solving such a task becomes significantly easier, from typing tens of actions to only editing a couple of thoughts, which enables new forms of human-machine collaboration. We note that such a policy edit on the go is difficult for ACT and previous RL methods, as a human cannot change the model parameters, and changing a few actions might not edit the rest of the model behavior. This paradigm is also more than human dialogue to update the goal or sub-goal. While editing ReAct thoughts can do these, it can also modify the model's internal belief, reasoning styles, or anything the flexible thought space supports for better task solving. We believe this is an exciting direction for human alignment and leave more systematic study as future work. B. Experiment details. B1 Hotpot QA fine-tuning details. For all fine-tuning, we use a batch size of 64. On Palm 8B, we fine-tune ReAct and ACT methods for 4,000 steps and Standard and CoT methods for 2,000 steps. On Palm 62B, we fine-tune ReAct and ACT methods for 4,000 steps and Standard and CoT methods for 1,000 steps. We find ReAct and ACT methods generally benefit from more training steps and more training data, while Standard and CoT methods degrade soon after fine-tuning. B2 AlfWorld IM style details. For the IM style ablation, the same expert trajectories used in ReAct are re-annotated with dense external feedback thoughts within these trajectories that limit ReAct IM to only think about 1, decomposing the current goal, and 2, the current sub-goal that needs to be completed. In particular, ReAct IM lacks thoughts that 1, determine when a sub-goal is completed, 2, determine what the next sub-goal should be, inducing the LLM to refer to its internal pre-training knowledge to identify where items can be within the environment. C prompts. C1 hot. Continued on next page. Action 3 finish, director, screenwriter, actor. Question: which magazine was started first, Arthur's Magazine or First for Women? Action 1 search, Arthur's Magazine. Observation 1, Arthur's Magazine, 1844 to 1846, was an American literary periodical published in Philadelphia in the 19th century. Action 2, search, First for Women. Observation 2, First for Women is a woman's magazine published by Bauer Media Group in the USA. 1. The magazine was started in 1989. Action 3, finish, Arthur's Magazine.
Table C.1 Summary. The table presents a series of questions and answers from the Hotpot QA dataset. It includes topics such as the elevation range of the Colorado orogeny, 1,800 to 7,000 feet, the inspiration behind the name of the Simpsons character Milhouse, Richard Nixon, and the documentary about Finnish rock groups, the Saimaa Gesture. It also covers the shared professions of Nicholas Ray and Elia Kazan, director, screenwriter, actor, the earlier founding of Arthur's Magazine compared to First for Women, and the similar work type of Pavel Dorovshin and Leonid Levin.
Question: were Pavel Urisan and Leonid Levin known for the same type of work? Action 1. Search Pavel Urisan. Observation 1. Pavel Samuilovich Urisan, February 3, 1898, August 17, 1924, was a Soviet mathematician who is best known for his contributions in dimension theory. Action 2. Search Leonid Levin. Observation 2. Leonid Anatolyevich Levin is a Soviet-American mathematician and computer scientist. Action 3. Finish. ReAct. Question: What is the elevation range for the area that the eastern sector of the Colorado orogeny extends into? Thought, let's think step by step. The eastern sector of Colorado orogeny extends into the high plains. High plains rise in elevation from around 1,800 to 7,000 feet. So the answer is 1,800 to 7,000 feet. Answer: 1,800 to 7,000 feet. Question: musician and satirist Ali Gortz wrote a song about The Simpsons character Milhouse, who Matt Groening named after who? Thought, let's think step by step. Milhouse was named after U.S. President Richard Nixon, so the answer is Richard Nixon. Answer: Richard Nixon. Question: which documentary is about Finnish rock groups, Adam Clayton Powell or the Sina gesture? Thought, let's think step by step. Adam Clayton Powell film is an African-American politician, not Finnish rock groups. So the documentary about Finnish rock groups must instead be the Sina gesture. Answer: the Sina gesture. Question: what profession does Nicholas Ray and Elia Kazan have in common? Thought, let's think step by step. Professions of Nicholas Ray are director, screenwriter, and actor. Professions of Elia Kazan are director, producer, screenwriter, and actor. So profession Nicholas Ray and Elia Kazan have in common is director, screenwriter, and actor. Answer: director, screenwriter, actor. Question: which magazine was started first, Arthur's Magazine or First for Women? Thought, let's think step by step. Arthur's Magazine was started in 1844. First for Women was started in 1989. 1844, Arthur's Magazine, is less than 1989, First for Women, so Arthur's Magazine was started first. Answer: Arthur's Magazine. Question: were Pavel Urisan and Leonid Levin known for the same type of work? Thought, Amenthasam. We'll think step by step. Pavel Urisan is a mathematician, Leonid Levin is a mathematician and computer scientist. So Pavel Urisan and Leonid Levin have the same type of work. Answer: yes. Observation 4. The High Plains are a subregion of the Great Plains. From east to west, the High Plains rise in elevation from around 1,800 to 7,000 feet, which is approximately 550 to 2,130 meters.
Code explanation. This algorithm is a step-by-step reasoning process to find the elevation range of the area where the eastern sector of the Colorado orogeny extends. It starts by identifying the Colorado orogeny as a mountain-building event in Colorado and surrounding areas. The algorithm then seeks information about the eastern sector, discovering that it extends into the High Plains, also known as the Central Plains orogeny. Finally, it focuses on finding the elevation range of the High Plains in the United States.
Thought 5. High Plains rise in elevation from around 1,800 to 7,000 feet. So the answer is 1,800 to 7,000 feet. Action 5. Finish 1,800 to 7,000 feet. Question: musician and satirist Ali Gortz wrote a song about the Simpsons character Milhouse, who Matt Groening named after who? Thought. The question simplifies to: the Simpsons character Milhouse is named after who? I only need to search Milhouse and find who it is named after. Action 1. Search. Observation 1. Milhouse Mussolini Van Houten is a recurring character in the Fox animated television series The Simpsons, voiced by Pamela Hayden and created by Matt Groening. Thought 2. Search goes on to tell who Milhouse is named after. Maybe I can look up named after. Action 2. Look up. Observation 2. Result if 1. Milhouse was named after U.S. President Richard Nixon, whose middle name was Milhouse. Thought 3. Milhouse was named after U.S. President Richard Nixon. So the answer is Richard Nixon. Action 3. Finish. Question: which documentary is about Finnish rock groups, Adam Clayton Powell or the Sima gesture? Thought: I need to search Adam Clayton Powell and the Sima gesture and find which documentary is about Finnish rock groups. Action 1. Search. Observation 1. Could not find Adam Clayton Powell. Similar: Adam Clayton Powell 3, 7th Avenue, Manhattan, Adam Clayton Powell Jr. State Office Building, Isabel Washington Powell, Adam Clayton Powell film, Giancarlo Esposito. Thought 2. To find the documentary, I can search Adam Clayton Powell. Action 2. Search. Adam Clayton Powell. Observation 2. Adam Clayton Powell is a 1989 film about the rise and fall of influential African-American politician Adam Clayton Powell Jr. It was later aired as part of the PBS series The American Experience. Thought 3. Adam Clayton Powell film is a documentary about an African-American politician, not Finnish rock groups. So, the documentary about Finnish rock groups must instead be the Saimaa gesture. Action 3 Finnish. Question. What profession does Nicholas Ray and Elia Kazan have in common? Thought I need to search Nicholas Ray and Elia Kazan. Find their professions, then find the profession they have in common. Action 1 Search. Observation 1. Nicholas Ray, born Raymond Nicholas Kienzle Jr., August 7, 1911, June 16, 1979, was an American film director, screenwriter, and actor, best known for the 1955 film Rebel Without a Cause. Thought 2, profession of Nicholas Ray, are director, screenwriter, and actor. I need to search Elia Kazan next and find his professions. Action 2 Search. Observation 2, Elia Kazan was an American film and theater director, producer, screenwriter, and actor. Thought 3, professions of Elia Kazan are director, producer, screenwriter, and actor. So professions Nicholas Ray and Elia Kazan have in common is director, screenwriter, and actor. Action 3 Finish, director, screenwriter, actor. Question, which magazine was started first? Arthur's Magazine or First for Women? Thought I need to search Arthur's Magazine and First for Women and find which was started first. Action 1 Search. Observation 1. Arthur's Magazine, 1844-1846, was an American literary periodical published in Philadelphia in the 19th century. Thought Arthur's Magazine was started in 1844. I need to search First for Women next. Action 2 Search. First for Women is a women's magazine published by Bauer Media Group in the USA. The magazine was started in 1989. 1844, Arthur's Magazine, is less than 1989, First for Women, so Arthur's Magazine was started first. Action 3 Finish. Question. Were Pavel Urisan and Leonid Levin known for the same type of work? Thought I need to search Pavel Urisan and Leonid Levin, find their types of work, then find if they are the same. Fever prompts. Original. Determine if there is observation that supports or refutes a claim, or if there is not enough information. Claim Nikolaj Coster-Waldau worked with the Fox Broadcasting Company. Answer supports. Claim Stranger Things is set in Bloomington, Indiana. Answer refutes. Claim Beautiful reached number 2 on the Billboard Hot 100 in 2003. Answer not enough info. New determine if there is observation that supports or refutes a claim, or if there is not enough information. Claim Nikolaj Coster-Waldau worked with the Fox Broadcasting Company. Action 1. Search Nikolaj Coster-Waldau. Observation first. Nikolaj William Coster-Waldau, born 27th of July 1970, is a Danish actor and producer. He graduated from the Danish National School of Performing Arts in Copenhagen in 1993, and had his breakthrough role in Denmark with the film Night Watch, 1994. He played Jaime Lannister in the HBO fantasy drama series Game of Thrones, for which he received 2 Primetime Emmy Award nominations for Outstanding Supporting Actor in a Drama Series. Coster-Waldau has appeared in numerous films in his native Denmark and Scandinavia, including Headhunters 2011 and 1,000 Times Good Night 2013. In the U.S., his debut film role was in the war film Black Hawk Down 2001, playing Medal of Honor recipient Gary Gordon. He then played a detective in the short-lived Fox television series New Amsterdam 2008 and appeared in the 2009 Fox television film Virtuality, originally intended as a pilot. Action 2 Finish supports. Claim Stranger Things is set in Bloomington, Indiana. Action 1 Search Stranger Things. Observation 1. Stranger Things is an American science fiction horror drama television series created by the Duffer Brothers. Set in the 1980s, primarily in the fictional town of Hawkins, Indiana, the series centers on a number of mysteries and supernatural events occurring around the town and their impact on an ensemble of child and adult characters. Action 2 finish. Claim Beautiful reached number 2 on the Billboard Hot 100 in 2003. Action 1 search Beautiful. Observation 1 could not find Beautiful. Similar, Beautiful, 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 A Beautiful Mind film, Beautiful, Christina Aguilera song, Life is Beautiful. Action 2 search Beautiful, Christina Aguilera song. Observation 2, Beautiful, is a song recorded by American singer Christina Aguilera for her fourth studio album, Stripped, 2002. Action 3, look up Billboard Hot 100. Observation 3, 1-3. The song peaked at number 2 on the Billboard Hot 100 in the United States, where it was certified gold for 500,000 units shipped. Action 4. Finish not enough info. Test determine if there is observation that supports or refutes a claim, or if there is not enough information. Claim Nikolai Coster-Waldau worked with the Fox Broadcasting Company. Thought Nikolai William Coster-Waldau appeared in the 2009 Fox television film Virtuality, so he has worked with the Fox Broadcasting Company. Answer: supports. Claim Stranger Things is set in Bloomington, Indiana. Thought Stranger Things is in the fictional town of Hawkins, Indiana, not in Bloomington, Indiana. Answer: refutes. Fever prompts continued from previous page. Claim Beautiful reached number 2 on the Billboard Hot 100 in 2003. Thought. The song peaked at number 2 on the Billboard Hot 100 in the United States, but not sure if it was in 2003. Answer: not enough info. ReAct. Determine if there is observation that supports or refutes a claim, or if there is not enough information. Claim Nikolai Coster-Waldau worked with the Fox Broadcasting Company. Thought. I need to search Nikolai Coster-Waldau and find if he has worked with the Fox Broadcasting Company. Action 1 search. Observation 1. Nikolai William Coster-Waldau, born 27th of July 1970, is a Danish actor and producer. He graduated from the Danish National School of Performing Arts in Copenhagen in 1993, and had his breakthrough role in Denmark with the film Night Watch, 1994. He played Jaime Lannister in the HBO fantasy drama series Game of Thrones, for which he received 2 Primetime Emmy Award nominations for Outstanding Supporting Actor in a Drama Series. Coster-Waldau has appeared in numerous films in his native Denmark and Scandinavia, including Headhunters, 2011, and 1,000 Times Good Night, 2013. In the U.S., his debut film role was in the war film Black Hawk Down, 2001. Playing Medal of Honor recipient Gary Gordon. He then played a detective in the short-lived Fox television series New Amsterdam, 2008, and appeared in the 2009 Fox television film Virtuality, originally intended as a pilot. Thought 2. Because he appeared in the 2009 Fox television film Virtuality, he should have worked with the Fox Broadcasting Company. Action 2 finish. Claim Stranger Things is set in Bloomington, Indiana. Thought I should search for Stranger Things and see if it is set in Bloomington, Indiana. Action 1, search. Observation 1. Stranger Things is an American science fiction horror drama television series created by the Duffer Brothers. Set in the 1980s, primarily in the fictional town of Hawkins, Indiana, the series centers on a number of mysteries and supernatural events occurring around the town and their impact on an ensemble of child and adult characters. Thought 2. The observation says that it is set in a fictional town of Hawkins, Indiana, so it is not set in Bloomington. Action 2 finish. Claim Beautiful reached number 2 on the Billboard Hot 100 in 2003. Thought I need to search the song Beautiful and find if it reached number 2 on the Billboard Hot 100 in 2003. Action 1 search. Observation 1 could not find Beautiful. Similar, Beautiful, 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 A Beautiful Mind film, Beautiful Christina Aguilera song, Life is Beautiful. Thought 2 From suggestions, I should search beautiful Christina Aguilera song to find the song. Action 2 search. Observation 2, Beautiful, is a song recorded by American singer Christina Aguilera for her fourth studio album Stripped, 2002. Thought 3, it does not mention Billboard, so I need to look up Billboard Hot 100 to find if it reached number 2 on it in 2003. Action 3, Lookup, Billboard Hot 100. Observation 3, result number over. The song peaked at number 2 on the Billboard Hot 100 in the United States, where it was certified gold for 500,000 units shipped. Thought 4. It only says the song peaked at number 2 on the Billboard Hot 100, but not if it was in 2003. I am not sure if this claim is true or not. Action 4 finish. C3 Web Shop. I would like a 3-ounce bottle of bright citrus deodorant for sensitive skin and price lower than $50.
Table 6 summary. The table presents a comparison between two approaches, ACT and ReAct, in a web shop experiment. Both methods involve searching for a 3-ounce bright citrus deodorant for sensitive skin under $50. ACT involves straightforward actions like searching and clicking, while ReAct includes reasoning steps before taking actions. Both approaches identify the same products, such as Bright Citrus Deodorant by Earth Mama and Ginger Fresh Deodorant by Earth Mama, each priced at $10 and $99. ReAct adds a reasoning step to evaluate options before proceeding with the purchase.
C4 Alfworld. You are in the middle of a room. Looking quickly around you, you see Cabinet 13, Cabinet 12, Cabinet 11, Cabinet 10, Cabinet 9, Cabinet 8, Cabinet 7, Cabinet 6, Cabinet 5, Cabinet 4, Cabinet 3, Cabinet 2, Cabinet 1, door frame china 1, countertop 1, dining table 1, drawer 1, fridge 1, garbage can 1, microwave 1, shelf 3, shelf 2, shelf 1, sink basin 1, stove burner 4, stove burner 3, stove burner 2, stove burner 1, and toaster 1. Your task is to put clean lettuce on the dining table. Go to fridge 1. The fridge is closed. Open fridge 1. You open fridge 1. Fridge 1 is open. In it, you see cup 3, egg 2, potato 3, and potato 2. Go to dining table. On dining table 1, you see apple L, bread L, butter knife 2, cup 2, fork 2, knife L, ladle L, lettuce L, mug 2, mug L, pan 2, pepper shaker L, spatula 3, tomato Z, and tomato L. Take lettuce L from dining table L. You pick up lettuce L from dining table L. Go to sink basin L. On sink basin L, you see apple ZL 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 ZL. Clean lettuce L with sink basin L. You clean lettuce L using sink basin L. Think now I clean lettuce 1. Next I need to put it on dining table L. Okay, go to dining table L. On dining table L, you see apple L, bread L, butter knife Z, cup Z, fork ZZ, knife LL. Ladle LL, mug ZZ, mug LL, pan ZZ, pepper shaker LL, spatula ZZ, tomato ZZ, and tomato LL. Put lettuce L on dining table L. You put lettuce L on dining table L. You are in the middle of a room. Looking quickly around you, you see a cabinet 1, a cabinet 12, a cabinet 11, a cabinet 10, a cabinet 9, a cabinet 8, a cabinet 7, a cabinet 6, a cabinet 5, a cabinet 4, a cabinet 3, a cabinet 2, a cabinet 1, a coffee machine 1, a countertop 1, a dining table 1, a drawer 1, a fridge 1, a garbage can 1, a microwave 1, a shelf 3, a shelf 2, a shelf 1, a sink basin 1, a stove burner 4, a stove burner 3, a stove burner 2, a stove burner 1, and a toaster 1. Your task is to put a clean lettuce in dining table. Think. To solve the task, I need to find and take a lettuce, then clean it with sink basin. Then put it in dining table. Okay, think. First I need to find a lettuce. A lettuce is more likely to appear in fridge 1, dining table 1, sink basin 1, stove burner from 1 to 3, cabinet from 1 to 13. I can check one by one starting with fridge 1. Okay, go to fridge 1. The fridge 1 is closed. Open fridge 1. You open the fridge 1. The fridge 1 is open. In it, you see cup 3, egg 2, potato 3, and potato 2. Go to dining table 1. On the dining table 1, you see apple 1, bread 1, butter knife 2, cup 2, fork 2, knife 1, ladle 2, lettuce 1, mug 2, mug 1, pan 2, pepper shaker 1, spatula 3, tomato 2, and tomato 1. Take lettuce from dining table. You pick up the lettuce from the dining table. Think, now I have lettuce. Next, I need to go to sink basin and clean it. Okay, go to sink basin. On the sink basin, you see apple and ladle spoon and tomato. Clean lettuce with sink basin. You clean lettuce using the sink basin. Think, now I have clean lettuce. Next, I need to put it on or in dining table. Okay, go to dining table. On the dining table, you see apple bread, butter knife, cup, fork, knife, knife, ladle, ladle, mug, mug, pan, pepper shaker, spatula, tomato, tomato. Put lettuce on or in dining table. You put the lettuce on or in the dining table. You are in the middle of a room. Looking quickly around you, you see cabinet 13, cabinet 12, cabinet 11, cabinet 10, cabinet 9, cabinet 8, cabinet 7, cabinet 6, cabinet 5, cabinet 4, cabinet 3, cabinet 2, cabinet 1, coffee machine 1, countertop 1, dining table 1, drawer 1, fridge 1, garbage can 1, microwave 1, shelf 3, shelf 2, shelf 1, sink basin 1, stove burner 4, stove burner 3, stove burner 2, stove burner 1, and toaster 1. Your task is to put clean lettuce on the dining table. Think, to solve the task, I need to find and take lettuce, then clean it with sink basin 1, then put it on the dining table. Okay. First, I need to find lettuce. Okay. Go to fridge 1. The fridge 1 is closed. First, I need to find lettuce. Okay. Open fridge 1. You open the fridge 1. The fridge 1 is open. In it, you see cup 3 egg, 2 potato 3, and potato 2. Think. First, I need to find lettuce. Okay, go to dining table 1. On the dining table 1, you see apple, 1 bread, 1 butter knife, 2 cup, 2 fork, 2 knife, 1 ladle, 2 lettuce, 1 mug, 2 mug, 1 pan, 2 pepper shaker, 1 spatula, 3 tomato 2, and tomato 1. Think, first I need to find lettuce, okay? Take lettuce 1 from dining table 1. You pick up the lettuce from the dining table. Think, I need to clean this lettuce using sink basin 1. Okay, go to sink basin 1. On the sink basin, you see apple, 2 ladle, 2 spoon 1, and tomato 3. Think, I need to clean this lettuce using sink basin 1. Okay, clean lettuce with sink basin. You clean the lettuce using the sink basin. Think, I need to put this cleaned lettuce on the dining table. Okay, go to dining table 1. On the dining table, you see apple bread, butter knife, cup, fork, knife, ladle, mug, mug, pan, pepper shaker, spatula, tomato, and tomato. Think, I need to put this clean lettuce on the dining table. Okay. Put lettuce on dining table. You put the lettuce on the dining table. D. Trajectories. D1 fever trajectories. We provide some trajectories produced by ReAct, CoTan-Act on several randomly selected examples from the fever dev set below. Search results are omitted to space.
Example 2491 code explanation. The algorithm evaluates the claim that the Bermuda Triangle is in the Pacific Ocean. It starts by planning to search for information about the Bermuda Triangle. Upon searching, it observes that the Bermuda Triangle is actually located in the western part of the North Atlantic Ocean. Based on this observation, it concludes that the claim is false and refutes it. Example 2491 code explanation. The algorithm evaluates a claim about the Bermuda Triangle's location. It starts by searching for information about the Bermuda Triangle. The search reveals that the Bermuda Triangle is associated with reportedly haunted locations, which implies it is not in the Pacific Ocean as claimed. Based on this information, the algorithm concludes that the claim is false and refutes it. Example 2491 code explanation. The algorithm evaluates the claim that the Bermuda Triangle is located in the Pacific Ocean. It uses a step-by-step reasoning process to verify the claim. By recognizing that the Bermuda Triangle is actually in the Atlantic Ocean, the algorithm concludes that the claim is incorrect and refutes it.
Example 2491.
Example 5908 code explanation. The algorithm evaluates the claim that Princess Mononoke is a film. It begins by planning to search for information about Princess Mononoke. After conducting the search, it observes that Princess Mononoke is indeed a film. Based on this observation, it concludes that the claim is true and supports it.
Example 5908.
Code explanation. The algorithm evaluates the claim that Princess Mononoke is a film. It begins by searching for information about Princess Mononoke. After conducting the search, it observes that Princess Mononoke is indeed a film. Based on this observation, it concludes that the claim is true and supports it. Code explanation. The algorithm evaluates the claim that Princess Mononoke is a film. It uses a step-by-step reasoning process to verify the claim. By recognizing that Princess Mononoke is a movie and movies are films, it concludes that the claim is true and supports it. Example 1951 code explanation. The algorithm attempts to verify the claim that Soyuz was part of the American space program. It begins by searching for information about Soyuz, which reveals that it is a transliteration. Since this does not confirm the claim, it proceeds to search for American space program, but finds no mention of Soyuz. Unable to verify the claim, the algorithm concludes with not enough info.
Example 1951 refutes.
Code explanation. The algorithm attempts to verify the claim that Soyuz was part of the American space program. It starts by searching for information about Soyuz, which reveals that it is a transliteration. Since this information is insufficient to confirm the claim, the algorithm concludes with not enough info. Code explanation. The algorithm evaluates the claim that Soyuz was part of the American space program. It uses a step-by-step reasoning process to analyze the claim. It identifies Soyuz as a Russian spacecraft and acknowledges that the American space program is NASA. The algorithm notes that NASA and Russia have collaborated on the International Space Station, leading it to conclude that the claim is supported. Table 3208 Summary. The table presents 3 different approaches to verifying the claim that Reign Over Me is an American film made in 2010. The ReAct approach correctly identifies that the film was made in 2007, thus refuting the claim. The ACT approach incorrectly supports the claim without verifying the date. The COTI approach also incorrectly supports the claim by assuming the film was made in 2010.
D2 ALF-World Trajectories. We provide an example trajectory of ReAct, ACT, and ReAct IM on the same ALF-World game. Pick clean, then place in Recept Knife countertop/trial T2190909 110445 675754. D2.1 ReAct Trajectory. ReAct is able to correctly find the knife, clean it, and then place it on a countertop. You are in the middle of a room. Looking quickly around you, you see 6 cabinets numbered 1 through 6, 1 coffee machine, 3 countertops numbered 1 through 3, 3 drawers numbered 1 through 3, 1 fridge, 1 garbage can, 1 microwave, 3 shelves numbered 1 through 3, 1 sink basin, 4 stove burners numbered 1 through 4, and 1 toaster. Your task is to put a clean knife in countertop. Think, to solve the task, I need to find and take a knife, then clean it with sink basin, then put it in countertop. Okay, think, first I need to find a knife. A knife is more likely to appear in cabinets numbered 1 through 6, drawers numbered 1 through 3, countertops numbered 1 through 3, fridge, garbage can, shelves numbered 1 through 3, sink basin, stove burners numbered 1 through 4, toaster. I can check one by one, starting with cabinets. Okay, go to cabinet number 1. On cabinet number 1, you see bowl number 1. Go to cabinet number 2. Cabinet number 2 is closed. Go to cabinet number 3. On cabinet number 3, you see glass bottle number 1. Go to cabinet number 4. On cabinet number 4, you see mug number 1. Go to cabinet number 5. Cabinet number 5 is closed. Go to cabinet number 6. Cabinet number 6 is closed. Go to drawer number 1. Drawer number 1 is closed. Go to drawer number 2. Drawer number 2 is closed. Go to drawer number 3. Drawer number 3 is closed. Go to countertop number 1. On countertop number 1, you see 2 lettuces, mug number 2, pepper shaker number 1, and spoon number 2. Go to countertop number 2. On countertop number 2, you see cup number 1, dish soap bottle number 1, glass bottle number 3, knife number 1, plate number 2, potato number 3, and statue number 1. Think, now I find knife number 1. Next, I need to take it. Okay. Take knife from countertop number 2. You pick up knife from countertop number 2. Now I take knife. Next, I need to go to sink basin and clean it. Okay, go to sink basin. On sink basin, you see fork, lettuce, and spatula. Clean knife with sink basin. You clean the knife using the sink basin. Now I clean knife. Next, I need to put it on or in countertop. Okay, go to countertop. On the countertop, you see lettuce, mug, pepper shaker, and spoon. Put knife on or in countertop you put the knife on or in the countertop. D2.2 Act Trajectory. Act is able to correctly find the knife, but tries to clean it using a sink basin before actually going to the sink basin. From there on, the model is unable to recover and is stuck repeating the same sequence of commands. With ReAct, an existing thought would have concretely identified that the knife had been taken and that the next sub-goal was to go to a sink basin to clean it. Act Elf World Trajectory. You are in the middle of a room. Looking quickly around you, you see Cabinet 6, Cabinet 5, Cabinet 4, Cabinet 3, Cabinet 2, Cabinet 1, Coffee Machine 1, Countertop 3, Countertop 2, Countertop 1, Drawer 3, Drawer 2, Drawer 1, Fridge 1, Garbage Can 1, Microwave 1, Shelf 3, Shelf 2, Shelf 1, Sink Basin 1, Stove Burner 4, Stove Burner 3, Stove Burner 2, Stove Burner 1, and Toaster 1. Your task is to put clean knife in countertop. Go to countertop 1. On the countertop 1, you see lettuce 2, mug 2, pepper shaker 1, and spoon 2. Go to countertop 2. On the countertop 2, you see cup 1, dish sponge 1, glass bottle 3, knife 1, plate 2, potato 3, and statue 1. Take knife 1 from countertop 2. You pick up knife 1 from the countertop 2. Go to countertop 1. On the countertop 1, you see lettuce 2, mug 2, pepper shaker 1, and spoon 2. Clean knife 1 with sink basin 1, nothing happens. Go to countertop 3. On the countertop 3, you see bread 3, butter knife 2, cell phone 1, credit card 1, fork 2, houseplant 1, knife 2, spatula 1, statue 3, tomato 2, tomatillo, and vase 2. Take knife from countertop 3, nothing happens. Go to countertop 2. On the countertop 2, you see cup 1, dish sponge 1, glass bottle 3, plate 2, potato 3, and statue 1. Take knife from countertop 2, nothing happens. Go to countertop 1. On the countertop 1, you see lettuce 2, mug 2, pepper shaker 1, and spoon 2. Clean knife with sink basin 1, nothing happens. Go to countertop 3. On the countertop 3, you see bread 3, butter knife 2, cell phone 1, credit card 1, fork 2, houseplant 1, knife 2, spatula 1, statue 3, tomato 2, tomatillo, and vase 2. Take knife from countertop 3, nothing happens. Go to countertop 2. On the countertop 2, you see cup 1, dish sponge 1, glass bottle 3, plate 2, potato 3, and statue 1. Take knife from countertop 2, nothing happens. Go to countertop 1. On the countertop 1, you see lettuce 2, mug 2, pepper shaker 1, and spoon 2. Clean knife with sink basin 1, nothing happens. D2.3 ReAct IM Trajectory. ReAct IM is able to correctly find the knife, but is unable to clean it as well. The LLM then gets stuck trying to place this knife on a countertop. One possible issue is the incorrect thought think, I need to find a clean knife, which seems to trick the LLM in believing that the knife is already cleaned. In ReAct, this sequence of sub-goals would be concretely captured by each thought. ReAct 1M Alf World Trajectory. You are in the middle of a room. Looking quickly around you, you see Cabinet 6, Cabinet 5, Cabinet 4, Cabinet 3, Cabinet 2, Cabinet 1, Coffee Machine 1, Countertop 3, Countertop 2, Countertop 1, Drawer 3, Drawer 2, Drawer 1, Fridge 1, Garbage Can 1, Microwave 1, Shelf 3, Shelf 2, Shelf 1, Sink Basin 1, Stove Burner 4, Stove Burner 3, Stove Burner 2, Stove Burner 1, and Toaster 1. Your task is to put a clean knife in countertop. Think, to solve the task, I need to find and take a clean knife, then put it in countertop. Think, I need to find a clean knife. Okay, go to countertop 1. On the countertop 1, you see lettuce, 2 mug, 2 pepper shaker 1, and spoon 2. I need to find a clean knife. Okay. Go to countertop 2. On the countertop 2, you see cup 1, dish sponge 1, glass bottle, 3 knife, 1 plate, 2 potato 3, and statue 1. I need to find a clean knife. Take knife 1 from countertop 2. You pick up the knife 1 from the countertop 2. I need to put this knife 1 on or in countertop 1. Okay, go to countertop 1. On the countertop 1, you see lettuce, 2 mug 2 pepper shaker 1, and spoon 2. I need to put this knife 1 on or in countertop 1. Okay? Put knife L on or in countertop L. You put the knife L on or in the countertop L. I need to put this knife L on or in countertop L. Put knife L on or in countertop L. Nothing happens. Think, I need to put this knife L on or in countertop L. Okay. Put knife L on or in countertop L, nothing happens. I need to put this knife L on or in countertop L. Put knife L on or in countertop L, nothing happens. D3 web shop trajectories. Get me a 16-pack of apple cinnamon freeze-dried banana chips and price lower than $0. Action, search, 16-pack apple cinnamon freeze-dried banana chips. Observation, back to search. Page 1, total results 50. Brothers All Natural Fruit Crisps, Strawberry Banana, 0.42 ounce, pack of $158.50. Moon Fruit Freeze-Dried Fruit Snacks. Fruit Snacks for Kids, Variety Pack, $18.99. Nature's Turn Freeze-Dried Fruit Snacks, Banana Crisps, perfect for school lunches or an on-the-go snack. No sugar added, non-GMO, gluten-free, nothing artificial, 0.53 ounce 6-pack, $12.99. Action, click B061. Observation, back to search. Prev, flavor name Asian pear, banana, Fuji apple and cinnamon, strawberry banana. Brothers All Natural Fruit Crisps, strawberry banana, 0.42 ounce, pack of 100. Price, $58.50. Rating, description, reviews, buy now. ReAct, action, search, 16-pack apple cinnamon freeze-dried banana chips. Observation, back to search. Page 1, total results, 50. Brothers All Natural Fruit Crisps, Strawberry Banana, 0.42 ounce, pack of $158.50. Moon Fruit, Freeze-Dried Fruit Snacks. Fruit Snacks for Kids, Variety Pack, $18.99. Nature's Turn Freeze-Dried Fruit Snacks. Banana Crisps, perfect for school lunches or an on-the-go snack. No sugar added, non-GMO, gluten-free, nothing artificial. 0.53 ounce 6-pack, $12.99. Action, think B002 is strawberry banana, not apple cinnamon. B004HP62 is fruit snacks, not freeze-dried banana chips. B092P6 is banana crisps, not apple cinnamon. I can check B09K6 first. Observation, okay. Action, click B92K. Observation, back to search. Prev flavor nameful, apple cinnamon, banana, cantaloupe, peach, pear, strawberry banana, sampler variety pack, mega variety pack, orchard variety pack. Size 0.53 ounce, pack of 6, 0.53 ounce, pack of 9, 0.53 ounce, pack of 10, 3 ounce, pack of 10. Nature's Turn freeze-dried fruit snacks, banana crisps, perfect for school lunches or an on-the-go snack. No sugar added, non-GMO, gluten-free, nothing artificial, 0.53 ounce, 6-pack. Price, $12.99. Rating A. Description, features, reviews, buy now. Action, think for 16-pack of apple cinnamon freeze-dried banana chips. The item has options apple cinnamon and 0.53 ounce, pack of 16. And seems good to buy. Observation, okay? Action, click. Observation, you have clicked apple cinnamon. Action, click 0.53 ounce, pack of 16. Observation, you have clicked 0.53 ounce, pack of 16. Action, E-more analysis. E1, success and failure modes analysis. We provide some examples corresponding to the success and error mode analysis given in SECR 3.3. Search results and non-representative steps are omitted to reduce space. Success, true positive.
Figure code explanation. The algorithm is a step-by-step reasoning process used to answer a question about which U.S. president, a U.S. Navy admiral, who collaborated with author David Chanoff, served under as ambassador to the United Kingdom. The process involves searching for information about David Chanoff and the admiral, William J. Crowe. It concludes that Crowe served under President Bill Clinton, providing the answer as Bill Clinton. Code explanation. This algorithm is a reasoning process used to identify the name of a sports team representing an Arizona university in a conference that includes areas like Arizona, California, and New Mexico. The thought process involves recognizing that the team is the Arizona State Sun Devils, which is then provided as the answer.
False positive.
Code explanation. The algorithm is a reasoning process used to determine which of two board games, San Marco or About Time, was released first. It involves searching for information about both games. The search for San Marco provides information about its historical context, while the search for About Time results in a reference to a 2013 film. Based on this, the process concludes that San Marco came out first. Code explanation. The algorithm is a reasoning process used to determine which university, Vanderbilt or Emory, was founded first. It involves comparing the founding years of both universities, Vanderbilt University in 1873 and Emory University in 1836. The conclusion incorrectly states that Vanderbilt was founded first, despite the earlier founding year of Emory University. This illustrates a reasoning error in the process.
Failure. Reasoning error.
Code explanation. This algorithm is a reasoning process aimed at finding the middle name of an actress who was cast alongside several other actors in the musical Hairspray. The process involves searching for information about each of the listed actors to identify the actress in question and then determine her middle name. However, the reasoning process is incomplete and does not reach a conclusion. Code explanation. The algorithm is a reasoning process used to determine who is older between Danny Green and James Worthy. It involves comparing their birth years. Danny Green was born in 1987, and James Worthy was born in 1961. The process incorrectly concludes that Danny Green is older because it mistakenly interprets the comparison of years.
Failure. Search error. ReAct question. What does the goddess associated with the goddess Frigg consists of? What tales? Thought 1. I need to search goddess Frigg and find its associated goddess. Action 1. Search. Observation 1. Could not find goddess Frigg. Similar. Frigg. Frigg and Freya common origin hypothesis. Freya, section relation to Frigg and other goddesses and figures. Ear, redirect from ear, goddess. Balder. Thought 2. I need to search Frigg instead. Failure, hallucination. Coat, question. What was the first year a scientific journal published by an organization located in the Bronx was published? Let's think step by step. The first year a scientific journal published by an organization located in the Bronx was published was 1916. Answer, 1916, label 1909. Failure, label ambiguity. ReAct, question. What nationality is the man who developed the dictator game? Thought 1. I need to search dictator game, find the man who developed it, then find his nationality. Action 1. Search game. Observation 1. The dictator game is a popular experimental instrument in social psychology and economics. Action 3. Search. Observation 3. Amos Nathan Tversky. Thought 4. Amos Tversky is an Israeli cognitive and mathematical psychologist, so the man who developed the dictator game is Israeli. Action 4. Finishraeli, label Israeli-American. Question. Kurt Fuller from Stockton, CA appeared in which American detective comedy drama television series created by Steve Franks? Thought. Let's think step by step. Kurt Fuller from Stockton, CA appeared in Psych. Psych is an American detective comedy drama television series created by Steve Franks. Answer. Psych, label. Psych is an American detective comedy drama.